In this video, we're going to discuss equilibrium reactions. When we write most reactions, we have this example. Methane plus dioxygen becomes carbon dioxide plus water. We have an arrow saying, hey, my starting materials on the left, they go to these products on the right. And this is the general idea for reactions. If we have a reaction like ammonia synthesis, dinitrogen plus 3 dihydrogens becomes 2 ammonias. This is indeed a reaction. It's why we are able to continue farming at the rate we have to feed the present population of humanity. We need lots of nitrogen to nitrate the soils. As all the plants that we grow, we then ship the food away from the farmlands to big cities on the coasts, depleting the soil. We need nitrogen. But this reaction implies that we can just combine dinitrogen and hydrogen to make ammonia. Truth is, this is not the case, because if you had ammonia just hanging out and you had 2 of them, they would break apart. If you start a tank of ammonia gas, you can create dinitrogen dihydrogen. If you start with a tank that's a mix of dinitrogen dihydrogen, you can make ammonia. Well, the molecule doesn't know what else is in its container, so any 2 ammonia molecules can go backwards. They don't have to be in a tank that started pure ammonia. What this means is that if you start with nothing but nitrogen and hydrogen, let's say you had 100 dinitrogens and 300 dihydrogens and no ammonias. You could go forward. You could say, hey, react 1, go down to 99 of these, go down to 297 of those, make 2 of these. And while your nitrogen, your hydrogen could keep doing this, the moment I have 2, I could go backwards. What you have here is a situation where you have 2 different reactions, a forward reaction and a reverse reaction. Truth is, all reactions can do this, and there's a way to show it, which is a double-headed arrow. There's a bunch of different arrows. You might see 2 separate arrows. You could see a double-headed arrow like that. They're all different representations of the same idea. That your starting materials can make products, but your products can just undo the reaction and go back to starting materials. Anytime you have a mixture, both are happening. And so we have competing reactions. They compete in different directions. There's a forward, which is our starting material going to products. And there is a reverse, which is products going to starting materials. Well, one characteristic that governed rates of reaction was concentration. As you use up material, as you do the reaction, you start running out of starting materials. If you did this long enough, you'd start decreasing quite a lot. You'd go down to 50 of this, 150 of that. So we'd have some numbers like this. I'd have 50 molecules of dinitrogen, 150 molecules of dihydrogen, and 100 molecules of ammonia. Well, if we had our original time 1, time 2, so on, time 50. We'll just say it's some amount of time later. The rate of reaction for the forward reaction is going to be slower. At time 1, I had an enormous amount of my starting materials. There was tons of them around. Chances were it was very easy for either of my starting materials to bounce and find the other reactant and react. But as things get consumed, as they're eaten up over time, well, now there's just less of them. They move and they might not find anything for a while. As this reaction has been occurring, we have lost starting materials because it's been reacting. That's lowered the concentration. As your starting materials get consumed, your concentration of them goes down, which means your rate goes down. So if we were to look at this over time and rate forward. Originally, it was happening so fast, but as we use up material, it just goes slower and slower and slower. There's less and less material around. If we think about our product, on the other hand, well, there's more of it. As time has continued, I have more. And so originally the rate reverse was nothing. There was no product. It could not go backwards. But over time, I started making product, and so it managed to have a rate. And this goes up and up and up and up. As you consume starting materials, the speed of reaction will go down. As you produce products, the speed of the reverse reaction will go up. Eventually, those two will meet. And this drawing is a little bit off on angles, so let me redraw like this. Because what will really happen is they will eventually meet. They don't actually pass each other. Rates of forward and reverse reactions will have one of them decrease, one of them increase until they are equal. Way out here, and for the rest of the line here, they are the same speed. Our rate forward equals our rate reverse. What this means is if you were to react and remove 10 of your starting materials and make 20 product, well, the product is getting rid of 20 product and making 10 starting materials. They're doing it at the same speed. If you give somebody 3 of something and they give you 3 back, and you look at how much you have, you go, oh, I have the same amount I had a minute ago. Once your rates are equal, they can't go past each other anymore. Anytime one of your reactions occurs, the other reaction also occurs and counters it out. This is equilibrium. Equilibrium is simply when the rate of your forward reaction is equal to the rate of your reverse reaction. And all reactions will eventually achieve this. Now, if we think back to our first example, when we had CH4 plus O2 going to CO2 and water, it is very rare that you just grow hydrocarbons, but plants do it. Granted, they make sugar instead of methane, but it's the same idea. And bacteria definitely produce methane as a product of this. You can do both directions, but one of them is significantly more likely. If we think about the energies for this, I have my starting material and my product. So CH4, O2, CO2, and water. There's a reaction path. There's a pretty big hurdle. But there's a bigger hurdle to go backwards. There's an energy of activation for the forward direction and a different energy of activation for the reverse. Depending on how big those differences are, you will favor going towards one side. And so if you have rate and time, you can have one drop really, really low, and they may eventually reach equilibrium, but they don't have to meet in the middle. You could very much move almost completely to product. You could destroy almost all of your starting material before you had your rates equal. So there are many reactions where we don't even notice that they are equilibrium. Methane burning is technically in equilibrium with carbon dioxide and water going backwards, but you're not likely to ever see that. Some reactions are very one-sided, some reactions meet nicely in the middle. It depends on this difference in activation energies. But this is the idea of an equilibrium reaction. You have two competing reactions, starting material going to products and products going to starting materials. As you consume your reagents, you will slow down that reaction. As you produce products, you will speed up that reaction. Eventually, they will be going at the same speed, and when that happens, your equilibrium is achieved. When that occurs, you cannot change the amounts of your chemicals anymore. So in those first few seconds, we might have seen some nitrogen disappear and some ammonia show up. But once we're to equilibrium, once we reach our equilibrium time, no matter how much longer you watch it, those amounts will no longer change. So while at time 50, our arbitrary endpoint, we said ammonia was at 100, if you go out to time 51, 52, or 2794, it continues to be the same amount of ammonia. At equilibrium, our concentrations will no longer change.